Hi everyone, and welcome to this lesson on synthesis and decomposition reactions. This is section 5.1 in the McGraw-Hill-Ryerson textbook. And the goal of this lesson really is to begin to discover how chemical reactions actually occur. How do we know what's going to happen? How do we know if things are going to break apart, if they're going to come together? And so that's going to guide us in this time together. The first thing we're going to note is that sometimes we'll see the states of the reactants and products written below each of those things. And so sometimes if it's a solid, it'll have an S by it. If it's an L, it'll mean liquid. If it's a G, it'll mean gas. And AQ means aqueous. That means it's simply dissolved in water. So moving on from that, we want to look into some of these details. And the first thing we want to look into is two examples. And these are things you're probably, well, the first one you're probably not super familiar with, but the second one you're very familiar with because we did a lab about 5 or 6 classes ago on this very thing. And so the first equation that we have here is pretty straightforward. It's carbon dioxide. And we know that carbon dioxide and water, we know H2O is water, that makes for us H2CO3, which is carbonic acid. Now you might be asking, well, I thought HCO3 was a hydrogen carbonate. Well, you'd be correct. But HCO3 is a polyatomic ion, meaning it has to combine with a metal in order to become a molecule. H2CO3 is already a molecule, and so this is called carbonic acid. So what you have in this situation is you have carbon dioxide and water coming together, so we'll find out they're synthesizing to become carbonic acid. The second equation that we have up there is something that we're familiar with probably from a lab we've done, and that is calcium hydroxide. And we have sodium carbonate. If you look that up, that carbonate is a polyatomic ion. And then we have calcium carbonate over here. And next to that, we have sodium. I deleted everything there. Calcium carbonate. Control Z doesn't work in this. And sodium hydroxide. And so what's happened there is it seems that the polyatomics have actually switched places. And so that's what we're going to see in a lesson tomorrow. But we'll make more connections with that at that point. But the point here is that things are happening. They're not staying the same elements in the same places in both the reactants and products. If you look at your periodic table, this is the chemistry BFF, I call this, best friend forever, for those doing chemistry. And so you can see all your polyatomic ions at the very bottom of your periodic table. I've listed those in a chart there. And then obviously you have all the information you need on the periodic table there. Moving on, first thing we need to remind ourselves, the next thing we need to remind ourselves of is that the evidence of a chemical reaction is found by 4 different things. One is that it's a formation of a gas, formation of a precipitate, which is a solid, and a color change. And that's what we see in the little test tube there on the right. We also have a change in odor. So if something starts to smell, that is the evidence of a chemical reaction. And lastly, the production of light and heat. So if any of those occur, it's a chemical reaction that has taken place. So how do we actually classify these chemical reactions? Well, the first one I've already hinted at, and that is that we can have synthesis reactions. A synthesis reaction occurs when 2 or more reactants combine to form a product that's more complex. So in general, it has the form of one thing plus another thing coming together to form a larger molecule in the end. So let's see what this actually looks like practically. Here we have hydrogen gas and oxygen gas becoming water. And this has been balanced. You see we have 4 hydrogen on the left, 4 hydrogen on the right, 2 oxygen on the left, and then 2 times the O, so 2 oxygen on the right. And so this is an example of something like we see with an exploding Pringles can. You can Google that to find the video, but I believe if you're watching this video in the class at Modo, it will also be posted as a link down below. Basically what happens is hydrogen burns off. You put hydrogen gas in a Pringles can. It burns off as you light up a hole in the top. the hydrogen gas burning off. At the same time, oxygen comes through a hole in the bottom. And right at the time that the hydrogen and oxygen meet at a ratio of 2 to 1, all of a sudden they will form water, and it will get so hot so fast that that water will immediately become water vapor, and the whole Pringles can will explode, shooting up high towards the ceiling. And so that's an example of a synthesis reaction. The hydrogen and the oxygen came together to form water. Another example of a synthesis reaction is this one here. We have nitrogen gas and oxygen gas becoming nitrogen monoxide. That is a covalent or a molecular compound. And then if we take the nitrogen monoxide and we combine that with more oxygen, what we get is nitrogen dioxide, which is something that contributes towards smog in our cities. You might be wondering, how do you know that why do you have N2, O2, H2? Why are those with 2? And here's the reason why. And I'll go back to this slide here in a second. The reason that we see these is because of something that we call the diatomic elements. You can see this on this slide, diatomic elements. Some people will refer to this as Berinkelhoff. I refer to it as a Canadian as the hockey stick and the puck. As you can see, we have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, and then hydrogen, which is way on the other side of the periodic table, that's just been brought here for the purposes of this. So you've got an upside down hockey stick and a puck. Those are your diatomic elements. What that means is that as an element by itself in nature, it will always be found as a gas, and it will always be found having 2 together. Oxygen, O2, N2, F2, Cl2, Br2, I2, H2. We're always going to see that when it's by itself in nature. Once it's put into a compound, it's not a diatomic element anymore because it's not an element anymore. It's now a compound. So that brings us to our second type of reaction, and that is instead of coming together, it's going to split up. And that's a decomposition reaction. A decomposition reaction occurs when a reactant breaks down into 2, not two, or more simpler compounds. So for example, well, just in general, A and B will break down to be one element or one compound plus another compound or element. And so we see this in, for example, this equation, which looks rather confusing, but if you know what C7H5N3O6 is, it is TNT. It's dynamite. So it's TNT, it's dynamite, and what that's going to become is it's going to become nitrogen gas, and it's going to become water, and that vaporizes right away when it explodes. It's going to become carbon monoxide, and it's going to become just carbon, which is soot. Now you might wonder, well, why doesn't it just explode? Well, we all know that for TNT to explode, it needs a catalyst. And that catalyst in this case is fire. We need to have fire. And so if we do have fire, that TNT is going to break down. And in fact, it doesn't just break down into 2 things, it breaks down into 4 things in this particular case. Now, just to reiterate some of these steps for doing chemical reactions, I just want to go over the top of this slide with you. It says, the first thing we want to do is identify the type of reaction. When we see a reaction, we should be able to tell, is it going to combine or is it going to split apart? And so based on the type of reaction, if we're told it's synthesis, we know it's going to combine, and if we're told it's decomposition, it's going to split apart. Then we're going to predict the product using the type of reaction as a model. And finally, we're going to balance that. Now, on the back of your chemistry BFF that I mentioned earlier, is the diatomic elements listed right there. And so you can use that, as we noted earlier, to just be able to remember what those are. We're going to get into the rest of the details on that BFF later in this unit. Let's do a few practice questions now to try to make sure we get this. These are all going to be synthesis reaction equations. Sodium metal reacts with chlorine gas. So there we have sodium and chlorine gas. Remember, chlorine is a diatomic element, and so it's Cl2. It's a gas in nature. And so before we get to the next one, let's just see how that's going to become. We know that when we have sodium and chlorine together, it becomes NaCl. And the way we got that is we knew that sodium had a charge of 1 plus, and we knew that chlorine has a charge of 1 minus. And when we do the cross-down method, or the crossover method, we see that we get Na1Cl1. And if we have 1s, we don't need to write anything there. The problem is that's not balanced right now. And so to balance that, we have to add a 2 here. That's now going to give me 2 CLs. And I have 2 CLs on the other side. And now I have 2 sodiums on the product side. So to get it balancing on the reactant side, I need to put a 2 there. So I have 2 sodiums and 2 sodiums, 2 chlorines and 2 chlorines. Now the next thing that we have is solid magnesium reacting with fluorine gas. Again, we have magnesium. It's not diatomic, so it's just magnesium by itself. But fluorine is diatomic, so it's fluorine gas. And so what we're going to see when we combine these is magnesium, we know, has a charge of, if you look at your periodic table, has a charge of 2 plus, and fluorine gas has a charge of 1 minus. When we cross those down, what we find is that we get Mg, not with a big spike, but just Mg, Mg1F2. And so this is going to give me MgF2. Right now the fluorines are balanced and the magnesium are balanced, so we don't need to do anything more with that one. Now we look at aluminum metal reacting with fluorine gas. Same thing as magnesium. We have Al plus F2, again, for the same reasons, because of the diatomic molecule. Aluminum has a charge of 3 plus. And so when we cross that down, Al 3 plus, and we know that fluorine has 1 minus. We cross those down, and we get Al1F3. Al1, we don't need to write the 1, F3. And so to balance that, the first thing I'm going to do is recognize that I have 3 fluorine on the one side and 2 on the other. So to get a common multiple, I'm going to multiply this side by 2 and this side by 3. So now that's going to give me 6 fluorine on both sides. Well, if I have 2 aluminum on the product side, then I need to put 2 on the reactants as well. So there we go. That is now the balanced chemical equation for those synthesis reactions. So now this next question says identify the type of reaction for each of the following synthesis or decomposition reactions and write the balanced chemical equation. Well, it should be pretty clear from these that if we have 2, we're going to synthesize. And if we have 1, we're going to decompose. I'm just going to write these short forms here. Again, we have 2, so we're going to synthesize. And then this one is going to decompose as well. And so now let's go ahead and actually do these. Nitrogen plus oxygen as a covalent compound is NO. And so to balance that, we just write a 2 in front of the NO. The next thing we have is barium carbonate. And barium carbonate is going to split apart. It's going to give us barium, and it's going to give us the carbonate, CO3. Now, neither one of those is a diatomic molecule, so it actually ends up being balanced right there. Now, this next one is cobalt and sulfur. And so cobalt, we're told we're going to use the 3 plus charge. Sulfur has a charge of 2 minus, and so when we cross those down, because it's an ionic compound, we get CO2S3. And so this becomes CO2S3. And then we have to consider how we're going to make these coefficients to be the same. We've got 3s in the product side, so we need 3s in the reactant side. We have 2 cobalt in the product side, so we need 2 cobalt in the reactant side. And the very last one is nitrogen triiodide. And so when we break this down, because it's a decomposition reaction, we're going to get nitrogen, which we know is a diatomic molecule, and iodine is also a diatomic molecule. So in order to balance this, we need to put a, again, look at the iodine, which has 2 and 3. So that would be a common multiple would be 3 and 2. So that would give us 6 iodine. And then we now have a balanced chemical equation because we have 2 nitrogen on the left and on the right, and we have 6 iodine on the left and on the right. So tomorrow we're going to look at single and double displacements, but for now it's just synthesis and decomposition, and you'll have some work and some videos to watch about some examples about how those work. Enjoy.